All right, so this is the AP Stats Linear Regression FRQ year 2005, number 3. And this is our walkthrough of how to do that FRQ. Originally, when I put this into the review packet, it looks like I somehow or another did not upload the first page of this. So this is what the first page should look like. It's about a railroad is interested in studying how fuel consumption is related to the number of rail cars for its trains on a certain between Oklahoma City and Omaha. Okay, so they sampled out 10 trains in this route and has yielded the data below. So this is their units per mile that they're able to travel depending on how many rail cars are attached. So like when there's 50 rail cars attached, it uses way more fuel, it looks like, than when there's 20 rail cars attached. It looks like it only uses about 58 units per mile, which kind of makes sense. The longer the train, probably the more fuel you're going to need to train. All right. Then the next thing they're looking at, which again was not in the original that I sent you, but I uploaded it on Google Classroom, is the scatter plot and then the residual plot. So for the first one, we are looking at the actual scatter. I can tell that because it's got the actual axis on the bottom, number of rail cars, so I'm going to have to remember about rail cars. And then fuel consumption. Do we know what fuel consumption units are? Yeah, it says units per mile. It doesn't even say whether it's gallons per mile or tankers per mile. I have no idea. Okay, so it's just units per mile. Okay, so here are the units per mile and fuel consumption. And that scatter plot, if I had to look at it, I would say that's positive linear, pretty strong, right? Okay, so if I'm looking at the form of these, that's kind of what I'm looking at. And then the residual, oh, look at that. The x's are the same? No, the x's have been fitted somehow. So we're starting at 50 and going up to 120. That's going to be interesting. So it definitely looks like the x's have been changed some. And then the y's, can't really tell what the residuals originally were from the original linear equation. The residuals definitely look nice. They look randomly assigned. That looks like just about as number of dots above the zero residual that are positive residuals is negative. Looks pretty random to me. So I'm pretty happy with all of this stuff, other than I noticed that the x's looks like that they have changed. All right, so I'm ready to go and answer some questions. So once again, more likely in 2020 is that they're going to just give us the actual equation. So up here they have told us that the fuel consumption is, and look at that, they've already given us our equation. So this would be basically like saying, well, it's 10.7 plus 2.15 x, right? That would be some version of that. Remember, the first number is our a, the second number is our b in the equation y equals a plus bx. Okay, so what they're saying is linear model appropriate for modeling these data? Clearly explain your reasoning. Okay, so for part A, what do you think we would say? Would you say that it looks linear would be appropriate? And we'd probably say linear is appropriate. Since the scatter plot, and you can't just call it the scatter plot, you gotta use context, of cars versus fuel consumption appears linear, strong, positive, with no apparent outliers. So remember, this is just for us, but we use the idea of soft, right? That it was saying it's strong. Outliers doesn't look like it has any. Form, it looks like it is linear, right? So I said linear. And then trend, it looks like it's positive. Cool, so we've covered all the main things of those. Was that the only thing that helped me to decide? No, there was some other stuff that helped me to decide that, right? One of them was that the residual looked fairly random, right? What else do we have? We have that that the residual looked relatively random. And then in the equation of the thing, we have R squared value that looks decently high, which means that there does appear to be most of the dots are accounted for by that linear best fit line. Okay, so those are going to be the three things basically that I'm going to talk about. So the second reason is the residual plot of rail cars. So was it really rail cars? Let's go back. Okay, so this went up to about 50 rail cars. Over here we've got 120 rail cars. So it definitely looks like they changed the X a little bit, and yet they didn't tell us how, right? We didn't get any X's that went up that far. So now I feel like I kind of have to avoid the residual plot because I don't know if that residual plot did anything. They didn't tell they adjusted it at any way, place, or anywhere else. So I wonder if that was a typo or if they meant to do that. Was there anything else in the residual plot? It says fitted values, but it doesn't really tell us what they did to fit them, right? So I'm going to guess that maybe they mislabeled the x-axis here on these. Do we have the same number of dots? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Do I have 10 dots up here? It looks like I do. I have 10 dots. Number of rail cars only went between 20 and 50, and the Y's went all the way up to 122. So the Y's don't look like they're a problem because residuals are just saying they're within 5. So if we're talking about 120, to be off by 5 is not a lot. And it looks like it's just they did something to the Y's and I'm not sure what it is. So I might want to say something along the lines of the residual plot of rail cars versus residual fuel provided, appears random and appropriate for a linear model. And lastly, what was the last thing? And r squared was equal to 96.7, and I'm going to use that as my last reason, 96.7%, which supports a strong relationship between the least square regression line and the points of data provided. Okay, really can't see why they would give us that residual plot that doesn't match the x-axis. So I'm just going to ignore that they made a mistake, or maybe I did. I don't see it anywhere. And I'm going to move on. Maybe we'll catch it later. All right, part B. All right, so part B says, suppose the fuel consumption cost is $25 per unit. So remember how I said that the fuel consumption only just said it was units per mile, right? So now they're saying for every one of those units, it's going to be $25. Okay, give a point estimate or a single value for the change in the cost per fuel per mile for each additional rail car attached to the train. Show your work. All right. So what we're looking at for part B, let's change the color here. All right, so they are now saying that we are now going to apply a cost to it. So before they just told us how much fuel we'd be using, right? So now it's going to be $25 for every fuel unit used. And they said, explain it as a average cost of fuel per mile for each additional rail car. So each additional rail car is the x's. So where did that come from? That sounds to me like it's slope, right? So 2.1495 would have been fuel units per mile per one rail car. Right? So if we would have explained that as slope, we would have said for every one rail car that increases, we would have an additional 2 units per mile, right? Now they're applying a dollar amount to those units per mile. So I'm going to now multiply that by $25. And I would get, if I multiply that together, I would get $53.75 dollars per mile for each individual rail car. Okay, so I'd be saying, so this is for part B, so I'd be saying something about the average cost, and I'm just repeating the question now back to them. The average cost of fuel per mile for each additional rail car, would be approximately 5375. Something like that. Cool? So that's how I'm going to answer B. C says interpret the value r squared again. So we're going to take that 96.7. I'm going to change my color here to something else. So 96.7. So part C, r squared equals 96.7%. So that means approximately 96.7% of the variation of Y, and Y was fuel consumption per mile per rail car. What was it? Fuel consumption per mile. Fuel consumption per mile can be explained by the linear relationship between fuel consumption in units per mile and number of rail cars. So we're basically saying that if we did a best fit line, about 96.7% of those dots that were on that graph for the best fit line would be closer to our best fit line than to a horizontal line through the mean. So we're saying if this is how good our linear fit is to anything else. Okay. All right. And then last question, part D, says, would it be reasonable to use the fitted regression equation to predict the fuel consumption for a train on this route if the train had 65 rail cars? Explain. Okay, so what am I looking for here? Is it okay to predict out to 65 rail cars? So they're asking me, am I going to be doing any extrapolation, or is it okay? So I go and look at my data. My data only goes up to 50. They're asking me to go out to here. Where is 65? 65 would be like out here. Is this okay to estimate all the way out to like 65? And that is definitely extrapolation. We only collected values between 20 and 50, right? So I just need to tell them that, okay? So lastly, in part D, I would say it is not reasonable to use the fitted data to estimate the fuel consumption for 65 rail cars, since our data only recorded fuel consumption for 20 to 50 rail cars. And I didn't go and actually check and see if 20 and 50, so I'm going to say approximately. 65 rail cars is extrapolation, which is a bad idea. Cool? Okay, so something like that. All right, so here is another linear regression problem where they're giving us a table of values. And I would say again for 2020, this is way more likely that you're going to see one of those table of values if they do a linear regression and ask you to explain some of those things. All right, so this is again 2005, number 3, and we'll post this with the video to your Google Classroom. All right, guys, talk to you later.